This lesson is on sets and equivalence relations. So a set is just a collection of objects. It's a naive, intuitive notion we have of things together. Clothes in a suitcase, flowers in a vase, stuff in a box. That's what a set is. And the basic notion in a set is membership. So a set has members or elements, and the notation X in S means X is a member or element of the set S. And if we have several sets, there's some simple operations we can perform on them. For example, union. So the union of two sets S and T, the notation S, and this is a U, T, this is the set of all X. You often write sets as elements inside of curly brackets. All elements X such that X is in S or X is in T. And we like to draw pictures of things. These pictures are sometimes called Venn diagrams. So if this is a set S and this is a set T, everything that's either in S or T or both is in S union T. We also define the intersection of S and T. So S intersect T, that's an upside down U. This is all elements X such that X is in S and X is in T. Here we have an or for union, but an and for intersection. And again, the picture is this is S and this is T. And this, the elements that belong to both, those are the elements in the intersection. So for example, if S is the set 1, 2, 3, 4, 5, and T is the set 2, 4, 6, 8, 10, so S union T is everything in both. 1, 2, 3, 4, 5, 6, 8, and 10. And S intersect T is everything in both. S union T is everything in one or the other. What elements are in both? Well, just the numbers 2 and 4. There's also an operation which is often useful called the symmetric difference. Of S and T. We write that with a delta. This is everything which is in X, every X which is in S, but not in T, union everything which is in T, but not in S. If we draw pictures of the two sets, so this These are the intersection. These are the elements of S which are not in T. These are the elements of T which are not in S. That's what makes up the symmetric difference. It's better to describe this in terms of what is called the complement. So the complement of S in T is, think of it as T take away S. This is every element X which is in T, which is not in S. So if this is S and this is T, the shaded region is T minus S. Everything in T which is not in S. And if you look at the symmetric difference, you can write this as everything which is S in S but not in T, union everything which is in T but not in S. Okay. These are all basic operations on sets. There's one very important notion I must mention, the idea of a subset. So we say S is a subset of T if every element X in S is an element of T. So you can think of it like this. Here's the set T, and sitting inside of it is this set S. So S is contained in T. Every element of S is an element of T. There's one very important, well, actually, there are two subsets that every set has. So first, S is a subset of itself. And second, there's a set which is called the empty set. The empty set, which is denoted like that, is the set that has no element in it. So like if your set is sets of clothes and you put them in a suitcase, if the suitcase is empty, that's the empty set. So the empty set is a set that has no element in it. And, well, I should say S is a subset of T. The notation for this is S is contained in T. So the empty set is contained in S for every set S. So the empty set is a subset of every set, and the whole set is a subset of itself. One more definition, very important. The power set of S, and everything has some notation. This is, I write a script P of S, is the set of all subsets of S. So let's look at some examples. Suppose S consists of just the numbers 1 and 2. So what are the power set? What is the power set of S? It's all subsets of S. The empty set, the set that just contains 1, the set that just contains 2, and the set itself. Actually, I should have taken an even easier example. If S is just the set that contains the number 1, the power set of S has 2 elements, the empty set and the set itself. Let's look at a harder example. So I'll call this example 1, this example 2. Example 3 is the set that consists of the numbers 1, 2, and 3. What is the power set of S? Well, we have the empty set. We have all the one element sets. We have all the two element sets. And we have the set itself. How large are the power sets? When we have a set with one element, the power set had two elements. When we had a set with two elements, the power set had four elements. With a set of three elements, the power set has 8 elements. So that is suggestive. And what does it suggest? Well, we like to have some notion of the size of a set. So the size of a set, and the more fancy word is the cardinality of a set S, is the number of elements in the set. And the notation is either S with absolute value signs around it, or we write card of S. So these are both notations for the number of elements in a set. And the number of elements can be finite or infinite. For example, if we take the set 2, 7, 13, and 29, call that S, the cardinality of this set is 4, contains 4 elements. And for the power set, there's a very nice theorem that says the following: if the cardinality of a set S is n, finite positive integer n, what about the power set of S? The cardinality of the power set of S is 2 to the n. So we already saw examples of that for n equal 1, 2, and 3. And we want to prove this is true in general. We don't have a lot of methods of proof at our disposal. One method is mathematical induction. So this is a statement about the integer n. Well, let's review again. What does it say in the case n equals 1? So S contains just one element. I'll call it x1. So the power set of S contains the empty set and the set itself. So the cardinality of the power set, so cardinality of S is 1, and the cardinality of the power set is 2, which is 2 to the power 1. So that's the starting point of our induction. And now we make the induction assumption. Assume the theorem is true for all sets of cardinality n. Let S be a set with cardinality of S equal to n plus 1. We have to show that S contains 2 to the power n plus 1 subsets. So suppose S consists of the elements x1, x2, xn, xn plus 1. How are we going to count the number of subsets? Well, divide the subsets of S into two classes or two sets. So first of all, we have subsets of S that contain xn plus 1, this last element. And we have subsets of S that do not contain xn plus 1. Let's count the number of these. It's easier to count the second group. A subset of this set S of the elements x1 up to xn plus 1 does not contain xn plus 1 if and only if we write that as this double-headed arrow, if and only if, say, subset T of S doesn't contain xn plus 1, if and only if T is a subset of x1 up to xn. A subset of S that doesn't contain this last element can only be a subset of the first n. And by the induction hypothesis, or the induction assumption, there are 2 to the n such subsets. In the other case, we look at the subsets that do contain xn plus 1. A subset T of S contains xn plus 1 if and only if T is a subset of x1 up to xn together with xn plus 1. So the number of these subsets is also 2 to the n. And then we make the following very simple observation. A subset of S either contains xn plus 1 or it does not contain it. So we've divided the subsets of S up into two groups. The ones that don't contain xn plus 1, there are 2 to the n of them. The ones that do contain xn plus 1, there are 2 to the n of those. Those collections have no elements in common. So the number of power sets of this set S with n plus 1 elements is 2 to the n plus 2 to the n, which is 2 to the n plus 1. And the proof. So that's a very nice proof. It's not very hard once you understand it, but you do need to spend a fair amount of time thinking about the proof and understanding it line by line and word by word until you can do the whole thing by yourself almost in your sleep. It's a very important proof to understand. two more definitions of concepts associated with sets are the following. So suppose we have A and B be subsets of a set S. The sets A and B are called disjoint if they have no elements in common. That means the intersection is empty. So a picture of that is, here you have the set S, here you have A, here you have B, and they don't overlap at all. These two subsets of S are disjoint. And subsets A1, A2, up to A sub k, let's say, finite collection of subsets of a set S are pairwise disjoint. If no two of them have any elements in common. So AI intersect AJ is empty for all integers I different from J, or all I less than J between 1 and K. So if this is the set S, this is A1, this is A2, this is A3, and this is A4. These sets are pairwise disjoint. They have nothing in common. Simply disjoint for a family of sets means subsets A1, A2, up to AK are disjoint if the intersection of all of them is empty. So I had defined earlier the intersection of two sets, and I defined the union of two sets. If we have K sets, the union of the K sets is the set of all X such that X is in AI for some I. Could be more than one, but any element which is in at least one of these sets is in the union. And the intersection of this finite family of sets is all X, such that X is in the ith set for all I. So what's an example of sets that are disjoint, but not pairwise disjoint? Let's say this is the set S. Suppose this is A1, this is A2, and this is A3. So A1 and A2 intersect. A1 and A3 intersect. A2 and A3 intersect. But there's no element that belongs to all three of them together. So this is a picture of sets that are disjoint, but not pairwise disjoint. If you wanted to write down a concrete example of such sets, you could, for example, let A equal 1, 2, 3, A1. Let A2 be equal to 3, 4, and 5. And you could let A3 be equal to 2, 5, and 6. A1 is in the first set, but not the others. Sorry, 1 is in the first set, but not the others. 2 is in these sets, but not this one. 3 is in these two, but not these. 4 is just here. 5 is in these two. 6 is just here. These sets are not disjoint, but they are pairwise disjoint. So this is an example of disjoint, but not pairwise disjoint sets. And the last pure definition about sets that I'm going to give is the following. A partition of a set S is a collection of pairwise disjoint subsets, say A1 up to AK, such that S is the union of these sets. So we have a finite collection of sets, S is the union of them, and none of these sets overlaps with any of the other. So for example, if this is S, this could be the set A1, this could be A2, this could be A3, this could be A4, this could be A5. So here's a set, here's a set, here's a set, here's a set, there's a set. And these sets don't overlap, but every element of S belongs to one of them. So this is what is called a partition of the set. It's a very important thing. Okay. Now, we've looked at sets and their subsets. So a subset is smaller than a set. There's a way, given a set, to construct a bigger set, or given 2 or 3 sets, to construct something out of them. And that's by a construction which is called the product. So the product of sets S and T is the set which is written as S times T, which is all ordered pairs, X, Y, where X is in S and Y is in T. So for example, if S is the set 1, 2, and T is the set A, B, C, what does the product set look like? Well, it's ordered pairs. The first element comes from S, the second element comes from T. So I could have 1A, 1B, 1C, 2A, 2B, 2C. This is all possible ordered pairs where the first coordinate comes from S and the second coordinate comes from T. It's actually exactly what you learned in pre-calculus, where you have R2, the XY plane, and you have all points XY. R2 is what we would call R cross R. It's the set of all ordered pairs XY, where X is a real number and Y is a real number. So the ordinary two-dimensional plane from calculus is an example of the product of 2 sets. Now you can take the product of a set with itself. S cross S, if S is, say, the set 1, 2, S cross S would be the ordered pairs 1, 1, 1, 2, 2, 1, 2, 2. And then we come to something which is extremely important in algebra, and it's the notion of what is called a relation. So a relation on a set S is what? Well, we want to say that certain elements of S are related to each other in some way. And so we're looking at pairs of elements, and we want to know whether the two elements in the pair are related. The set of all pairs is S cross S. So a relation on a set S is, and this is the official formal definition, a subset, I write it as script R, of S cross S. And we say that elements X and Y in S are related if the ordered pair XY belongs to R. So let's take an example. Suppose we take Z is the set of all integers, positive, negative, and 0. And suppose we let script R contained in Z cross Z. So Z cross Z is pairs of integers. And so that R consists of all pairs XY in Z cross Z such that X minus Y is even, an even integer. So for example, 719 is in R, minus 6, 100 is in R. Again, the difference is even in all these cases, but 1, 2 is not in R. Because 1 minus 2 is an odd number, it's not an even number. So this is a relation. And relations can have certain properties, or I should say maybe they do and maybe they don't. So one property of a relation is called being reflexive. A relation is reflexive if every element is related to itself. Maybe I should just make sure I introduce some notation. So we say that X, I'll do a squiggle with a little subscript I. This means X is related to Y, or the pair XY is in the relation. So X is related if every element is related to itself. We say that the relation is symmetric, capital letters because it's so important, if whenever X is related to Y, that implies Y is also related to X. And finally, we say a relation is transitive if whenever x is related to y and y is related to z, that implies that x is related to z. So some relations are reflexive, some are symmetric, some are transitive, some have two of these properties but not the third, and sometimes a relation has all of these properties. And that is a very important kind of relation. And we say it's called an equivalence relation. So an equivalence relation on a set X is a relation that is reflexive, symmetric, and transitive. It's a relation that has all three of these properties. What's an example? Well, the example I gave earlier, where we say that in the set of integers, the relation x is related to y if x minus y is even, is an equivalence relation. Why is that? Well, for every integer in z, x minus x is 0, and 0 is an even number. So x is related to x. What about symmetry? Well, if x, y are in z, and x is related to y, then x minus y is even, which implies that y minus x, which is minus the number x minus y, is even. Because if a number is even, so is its negative. So y is related to x. So x related to y implies y is related to x. And what about transitivity? So suppose x is related to y. That means x minus y is some even integer. I'll write it like 2a. And if y is related to z, then y minus z is an even integer. I can write it as 2b. Add these equations. You get x minus z is 2a plus 2b, which is 2 times a plus b, which is even. So therefore, x is related to z. So this is an example of an equivalence relation. So we will come back to equivalence relations over and over again in the in this course. But I wanted to make sure that as quickly as possible, you get to see the definition of an equivalence relation, and we will learn a lot more about these things. And that is exactly what I wanted to do in this lecture. So we are done.